Hello students. In this video we're going to go through a proof as to why Euler's formula is valid. Now I'm going to do this in the context of existence and uniqueness for initial value problems. The most common proof you'll see uses Taylor series expansion of the exponential, the sine, and the cosine. And because of uniqueness of limits, the uniqueness of limits of the partial sums, you'll get the e to the I t is equal to cosine t plus I sine t as a result. I'm not going to do that proof. You could probably see that proof in just about any calculus text. I'm going to focus on a proof that's in the context of differential equations and initial value problems. So I'm going to consider this initial value problem, z prime minus iz equals 0. I is square root of minus 1, that's the imaginary number I. Z of 0 will equal to 1 for this initial value problem. So what I'm going to do is I'm just going to solve this by separation of variables. So clearly e to the it is going to satisfy this differential equation. You could just even plug it in, the derivative of z prime, the derivative of z with respect to t, the I pops down, so you get an I e to the it minus I, and then you plug the z in there and you get e to the it and you get 0. And then of course z of 0 is equal to 1, so z of 0 is equal to e to the I times 0, but I times 0 is 0, so e to the 0 is equal to 1. All right, verified. So this complex exponential is indeed the solution to this initial value problem. Now this initial value problem, it only has one solution. Okay, that's the uniqueness theorem. So notice that cosine plus I sine here also satisfies the initial value problem. Let me verify that for you. Here I have z prime minus iz equals 0. I just rewrote the ODE over here on the right hand side, or in this right column here. And I'm just going to plug in my proposed solution into this ODE. So I have to take the derivative of this expression in the parentheses, and this expression in parentheses I'll leave alone. So when I take the derivative of cosine, I get minus sine. I take the derivative of sine, I get cosine. That's what the prime does. So I just distributed the derivative operator. I distribute the minus I to each of these terms. So I get a minus I cosine, I get a minus I times I, which is a minus I squared sine of t. Now watch what happens with the cancellation. Of course the cosines are going to cancel, and then notice that I squared is minus 1, but I had a minus sign, a minus 1 sitting in front of this. So this is going to be a minus, minus is going to give us a plus 1. So then you're going to see that the signs cancel, because this is going to be a plus sign. Guess a plus sign is in the sine function and a plus sign is a SIGN sign. So minus sign plus sign is equal to 0. So indeed that satisfies the ODE, and then if I plug 0 in to this proposed solution, I should get 1. That's what my initial value is telling me. Cosine of 0 is 1, sine of 0 is 0, I times 0 is 0, so 1 plus 0 is equal to 1. So it satisfies the initial condition as well. And by the uniqueness theorem for initial value problems, the solution to this IVP, this initial value problem, must be unique. That means that what I have boxed in here, this proposed solution, must equal this solution we got from separation of variables. So if I put those together, I get that e to the it is equal to cosine t plus I sine t. All right? Good luck.